Buenos días, a nombre del comité organizador les damos la bienvenida y gracias por estar en esta celebración en honor de Javier Gómez Montt, que han organizado sus alumnos, sus colegas, sus amigos. Esperamos que lo aprovechen y sea útil. Quisiera agradecer al CIMAT, a CONACYT, al Instituto de Matemáticas, al Centro de Ciencias Matemáticas de la UNAM, que aprovechamos para felicitarlo porque es un nuevo instituto que se ha creado, al Departamento de Matemáticas de la Universidad de Guanajuato, a la División de Ciencias Básicas e Ingeniería de la Universidad de Juárez, a la ISA, el Laboratorio Internacional Salomón Lefschetz, a la Sociedad Matemática Mexicana, al Clay Institute y al ICTP por el apoyo que nos dieron para que ustedes puedan estar aquí, ¿sí? Van a tener unas palabras del director del CIMAT, dando la bienvenida.
Gracias. So it's my pleasure to welcome you all to this workshop and conference on the occasion of the 60th anniversary of Javier Gómez Montt. I will continue in Spanish. Voy a tener el gusto de ser el primero en felicitar públicamente a Javier Gómez Montt por su cumpleaños 60. Felicidades, Javier. Y todos aquí saben quién es Javier Gómez Montt, si no, probablemente no estarían aquí, aunque también pueden estar atraídos por las pláticas que los conferencistas, que es una muestra más del poder de atracción del nombre de Javier Gómez Montt en el mundo. Pero déjenme decir algunas palabras al respecto de quién es Javier Gómez Montt. Javier es una de las personalidades más importantes de las matemáticas mexicanas y probablemente de la ciencia mexicana. A través de sus trabajos de investigación, que son variados, muy ricos en temas, en revistas muy importantes, ha marcado ya una pauta de alto nivel en las matemáticas mexicanas. A través de la formación de estudiantes que ya cuentan varias generaciones, ya eres que abuelo, bisabuelo, académicamente hablando, y del otro tipo no sé. En fin, a través de sus conferencias de divulgación, de popularización de las matemáticas, que se han vuelto famosas por lo atractivo y simpáticas y divertidas que logra proyectar Javier en sus pláticas. En fin, a través de todos estos asuntos, Javier se ha vuelto un referente de las matemáticas mexicanas. Pero para CIMAT significa todo esto y mucho más. Javier Gómez Montt ha sido uno de los motores más importantes en la creación de los posgrados de CIMAT. Ha sido forjador de generaciones que ahora forman parte de CIMAT. A Javier se debe el impulso de la internacionalización de CIMAT, internacionalización que se refleja en que es el centro más importante de acontecimientos matemáticos, de organización de eventos, organización de reuniones de alto nivel, organización de talleres, de escuelas, en fin. A Javier se debe la creación del CIMATEL, que ha sido no solo, yo creo que CIMATEL significa no solo el que pueda hacerse reuniones de manera económica, se trata de referentes donde la gente se refiere, se ubica en un lugar. Se habla del lugar del CIMATEL, del CIMAT en el mundo entero, gracias a los aportes de Javier. En fin, creo que Javier es una gran parte del alma del CIMAT, del alma y la mente de CIMAT. Entonces creo que felicitar a Javier, también hay que felicitar a CIMAT por tener a Javier entre sus miembros. Felicidades, Javier. And then officially, let me open the words of this workshop. I hope you enjoy your stay in CIMAT. I'm sure you will enjoy, and you will benefit of the several courses and the talks in the conference next week. So thank you.
Thank you.
You have your
Okay. It is an honor and pleasure for me to open this wonderful conference dedicated to Javier. I have very nice personal remembrance related to CIMAT. 20 years ago, Javier invited me with two students of mine, and we had wonderful time here. And since then, I visited Mexico many times, and it was very inspiring. And Laura is the mathematical daughter of Javier, and at the same time, she is a mathematical daughter of mine. And in this sense, we are, in a sense, relatives with Javier. Now, the first table is congratulation in Russian. An ancient Russian congratulation sounds многое лето, which means many years, and it is sang in an ancient manner. I will not sing, but I will pronounce многое лето, многое лето, многое лето. We will discuss polynomial foliations, phase portraits of polynomial differential equations in the complex projective plane. The plan of the talk is the following. The first part will be quite introductory and very well known to experts. I will address mainly to the part of the audience which is far from the subject, just to give an impression of the whole field. And the second part will be new results and problems. So I start with a very introductory information that in 1937, Andronov and Pantryagin discovered that if you consider a polynomial vector field in the real plane, it is generic in a sense, and you slightly perturb it, then the general picture of the phase portrait is not seriously changed, stays practically unchanged. And this property of phase portraits of vector fields was called structural stability. What about the complex plane? This question was not discussed until 60s, and the first example is to consider a Hamiltonian vector field which has a polynomial first integral whose phase portrait in the complex plane is just splitting of the plane to the Riemann surfaces, which are level curves of the polynomial. Once again, if the polynomial is generic, then the topology of this complex phase portrait will not be changed if you change the polynomial. Once again, this refers to integrable polynomial differential equations. What about non-integrable differential equations? Some experts believed that the answer will be the same, but even a simplest example of another kind of integrable differential equation, linear one with one-dimensional variable z, shows that the topology of the phase portrait in the zt plane is no more structurally stable. So this is a one-dimensional Fuchsian equation which may be easily solved, and when you make a circuit around the pole aj, then the solution z gets a multiplier equal to this new j, and therefore the monodromy group occurs. This is a representation of the fundamental group of the punctured sphere with the poles deleted. And this monodromy group appears to be a topological invariant of the phase portrait of this linear equation. So if two linear equations like that are topologically conjugated, that is, there is a homeomorphism of the ZT plane that brings one phase portrait to another one, then there is a homeomorphism that brings the monodromy map of one equation to the monodromy map of another equation. This homeomorphism of C to C conjugates one multiplication corresponding to one equation and another multiplication corresponding to another equation. And this is one and the same homeomorphism for all the generators, better to say for all the elements of the monodromy group. So, if you slightly perturb a group G with generators, this is a notation for a group with generators in the parentheses. If you slightly perturb the generators, then you obtain this property that the group will be dense in C star. And topological conjugacy of two such groups, it is an easy fact, will be in fact very similar to an automorphism of the multiplication group C star. It will be just a constant factor times this automorphism. And the automorphism of C star has this form. And therefore, you cannot say that if two groups like this are topologically conjugated, then the conjugacy is just multiplication by a complex number. No, it is multiplication by a complex number times this function. When beta equals 0, then this is really multiplication by a complex number. Now, this is about linear case, and even for Fuchsian equations that are very simple, we have a conclusion that two generic Fuchsian equations have non-topologically equivalent phase portraits in the ZT plane. Because we have many free parameters, for instance, new J's in the monodromy group are free parameters. And only one free parameter is the conjugacy, this exponent beta. So we can change the monodromy group in such a way that we will not be able to find beta. So there is no structural stability even in this simple case. Let us now switch for a while from phase portraits to one-dimensional groups. In the Fuchsian case, we had the monodromy group, which is a finitely generated subgroup of C star. Now consider for a while with no relation to differential equations. Now consider a finitely generated local object like this. That is a finitely generated group with generators which are germs of conformal maps of the complex plane into itself with 0 fixed point. That is, we start with a linear term and then there are nonlinear terms. And we consider two finitely generated groups of germs. The question is, what about their topological conjugacy? The question is very similar to the previous one about the topological conjugacy of linear groups. And The lemma here claims that if two generic groups that is having the properties, the groups have the properties that may be obtained by a small perturbation. If two generic groups are topologically conjugated, then they are analytically conjugated and vice versa. So for me, it was a key point in the understanding of the rigidity of complex foliations. Two objects are topologically conjugated. This is supposed, and as a conclusion, we get that they are analytically conjugated. So allow me to share with you my recollections, personal recollections. When a person becomes older, he more and more likes to share the memories of his youth with people. I was thinking on this problem for very long. And once I thought about it when I was in the bus that brought me from the university to home, that is from my students to my children. And when the bus was making a U-turn around the Leninsky Prospect, a large highway in Moscow, I understood that the lemma that I claimed is correct and may be proved in the following two steps. So the steps follow. The first step is that if a homeomorphism conjugates two finitely generated groups of germs of conformal mappings, then the same homeomorphism conjugates their linear parts in special charts. That is, you take a special chart which linearizes one of the germs, then in this chart you take the linear group with these generators, and it may be proved that the same H conjugates these two groups as well. So the same H conjugates two linear groups. Therefore, this H is of the form that I presented above. Now, let us make use of nonlinearity. A nasty function like this, it is nice when beta equals to 0 and nasty from the point of view of complex analysis otherwise. If such a nasty function conjugates two generic nonlinear germs, for instance, two germs whose two jets do not commute, that is, this difference is of order z squared, then a map of that nasty form that conjugates these two germs must mandatorily be nice, that is, has beta equal to 0. This is an easy calculation. And these are two steps of the proof of this key lemma. The paradigm of the whole my talk is, if two objects related to holomorphic dynamics are topologically conjugated, then they are holomorphically conjugated. And this lemma is the first fact of this type, is if two generic finitely generated groups of complex germs are topologically conjugated, then they are analytically conjugated. So it was the first result of this type. This is the paradigm that I said, but it is stated here in a stronger form. If we have two generic complex foliations of the complex projective space, not necessarily of a plane, then topological conjugacy implies affine conjugacy. This is in no way a theorem, and it would be great if such a theorem would appear at least for some particular class of foliations. But there are weaker statements in this spirit, and what follows is a realization of this paradigm in a sense. Let us discuss the first possible accurate definition that is a weaker realization of the paradigm above. A polynomial foliation in the projective plane, AN means polynomial foliation given by a polynomial vector field of degree n in a fixed affine neighborhood of CP2. So we have a distinguished infinite line. A polynomial foliation of this class is absolutely rigid, provided that there is a neighborhood of this foliation, the first neighborhood, and a neighborhood of identity in the space of homeomorphism of the complex projective plane into itself, such that if any foliation from the first neighborhood is conjugated to our foliation f by a homeomorphism from the second neighborhood, then this foliation is affine equivalent to f. So if there are two nearby foliations and they are conjugated by a homeomorphism which is close to identity, then this may happen only if these two foliations are affine equivalent. So the theorem proved more than 30 years ago claims that generic polynomial foliations of degree 1 are absolutely rigid. I will say a few words about the genericity assumptions. What is assumed about the foliations? I have not yet said what is the relation between complex foliations and finitely generated groups of germs. The relation is that any polynomial foliation of the class that we consider has an infinite leaf. The infinite line is a leaf of the foliation. Better to say the infinite line with singular points deleted. And there are n+1 singular points where n is the degree of the polynomial. When you make circuits around these singular points, you get a so-called monodromy group of the foliation and generate a dense subgroup of C star. For instance, monodromy groups for which all the linear parts are identities, that is, for which all the germs are parabolic, is forbidden by this genericity assumption, and this is the trouble in a sense. Two jets of some two germs do not commute, as it was in the previous lemma. And the last assumption is not about behavior at infinity, but about behavior near all singular point, whether either finite or infinite. This assumption is that there is no local analytic first integral. Definitely a genericity assumption. And under these assumptions, the previous theorem works. But the first theorem was, the first assumption was too strong. From the very beginning, there was an idea to make a weaker assumption. My graduate student of end of 70s, Arseniy Sherbakov, proved that in fact you do not need the group to have dense, to generate dense subgroup of linear parts. it's sufficient to assume that the group of germs is non-solvable. And if two groups of germs of conformal maps are non-solvable and topologically equivalent, then they are analytically equivalent. This is the result of Arseny-Sherbakov of 84 and Isao Nakai of 94. The proof of Nakai, I guess, is more readable. Here I just recall what non-solvability means. Non-solvability is a general algebraic notion, and I do not recall the general definition. In fact, for groups of conformal germs, non-solvability may be defined in a simpler way. You have a commutant of the group, and if this commutant is not an abelian group, then the group of germs is unsolvable. And this may be taken as a definition of a non-solvable group of germs. So now let us go back to absolute rigidity. We are again dealing with polynomial foliations in the complex projective plane. And the remark here is that topological equivalence of two generic foliations that satisfy genericity assumptions above implies analytic equivalence of their monodromy groups at infinity. So this is a bridge between foliations and finitely generated groups. We have some statement about groups. Using this remark, we make a conclusion for foliations. Now, let us go closer to the future frames about Xavier's contributions to the problem. In fact, the definitions given here became explicit only in the works of Javier, though they appeared, they were used in the proof that I discuss now. A family of foliations Ft, that is polynomial foliations that depend analytically on a parameter from a neighborhood of 0. This family is topologically trivial, provided that all the foliations are topologically equivalent, and the conjugacy between the main foliation that corresponds to the 0 value of the parameter and the other foliations is continuous with respect to the parameter. So this is topological triviality, and in the very same way you can define affine triviality, holomorphic triviality of a deformation of a foliation, and affine triviality is also defined here. You should just replace topological by affine 2 times. Now, the good term integrable deformation appeared very recently, though the notion is old. Suppose that you have a topologically trivial deformation depending on one parameter. You can even think about a picture in the real domain. So a 2-dimensional foliation and a 1-dimensional real parameter. You have a family of copies of the real plane corresponding to the parameter values, and you have a phase portrait corresponding to the 0 value of the parameter, and then you change the parameter. And there is a homeomorphism that takes this phase portrait, changes it, as a homeomorphism does, and brings to a phase portrait of another foliation in another copy of the plane that corresponds to the t-parameter value. Fix one phase curve in the original phase portrait. you will have a family of images of this phase curve. And when the parameter changes, this family of images saturates a two-dimensional surface. And in fact, whenever you have a topologically trivial deformation, you have sort of a trace foliation. The leaves of this foliation are obtained as follows. You take the phase curve, the leaf of the original foliation. This is the leaf of the original foliation through P. You take the homeomorphism depending on the parameter T. You take the union of all these phase curves, and you place a curve corresponding to the T parameter value in the copy of the plane that corresponds to the same parameter value. So this is a surface in the total space of the family, in the phase space multiplied to the parameter space. And this may be called a trace foliation. And this trace foliation occurs any time when you deal with a topologically trivial foliation. Now we want to distinguish the case when this trace foliation is especially good. It is called integrable if all the leaves of this trace foliation we are in the analytic context, are analytic manifolds, analytic surfaces, and depend analytically on the initial condition. So this foliation, briefly speaking, this foliation is holomorphic. This is the meaning of this definition. Once again, when you have a topologically trivial deformation, you always have a trace foliation with leaves of dimension 2 if you have a one-dimensional parameter of the family. And the foliation is integrable if this topological foliation with two-dimensional leaves is in fact holomorphic. The following lemma, any topologically trivial deformation of a generic foliation of the class an polynomial of degree n is integrable. This lemma is one of the key ingredients in the proof of the absolute rigidity theorem. And this lemma follows from the property of monodromy groups. The previous key lemma that I discussed first claims that when two monodromy groups, generic monodromy groups at infinity, I claim stay it in a slightly different terms, are topologically equivalent, then they are analytically equivalent. And this analytic equivalence of monodromy groups at infinity implies integrability of a topologically trivial foliation. And the second lemma claims that any integrable deformation of a generic foliation is affine of our class is affine equivalent, is affine trivial. So probably I give too much details, so those of you who are already tired may relax. I should finish soon with details and come to more general matters. Now I finish with details. An integrable deformation is generated by a holomorphic one form. And this one form is just sort of extension of the family of forms that determine our family of foliations. And by the genericity condition implied to the foliation F0, required from the foliation F0, we deduce that the third coefficient in this form is just in the ideal generated by the first two coefficients. An easy calculation of degrees shows that the coefficients in this ideal are of degree 1. Hence, a vector field like this is tangent to the leaves of the integrable deformation. So we have sort of a flow that produces the topological equivalence between the foliations of the family. This is a flow of a vector field V like this. The T component is 1, so this flow brings the 0 copy to the T copy of the phase space of the plane. And it brings the phase portrait of the original foliation, it brings the original foliation to the parameter T foliation. And as A and B are of degree 1 in Z and W, the phase flow of this, the phase flow transformation of this vector field is affine, and we are done. So integrability implies affine triviality as explained here. This is the frame that shows the argument already pronounced. So the last step is to pass from non-absolute rigidity to deformations. This previous discussion was about the foliation and its topologically trivial deformations. It appears, and this is a straightforward consequence of the definition, that if the foliation is not absolutely rigid, then it admits a topologically trivial deformation. And as before, it is proved that this deformation is affine trivial, and therefore, or close foliations topologically equivalent to the given one are affine equivalent to it. So this is a long story of the old times, now closer to the new times. Javier gave quite an alternative approach to the study of the rigidity problems in comparison with what was done here. And as his approach is alternative to mine, I give only a brief summary of Javier's results. For generic polynomial foliation in CP2 having an algebraic leaf, any topological trivial deformation parameterized not necessarily by one complex parameter in a neighborhood of 0, but by a reduced analytic space is holomorphically trivial. So this is another rigidity result about foliations. Now for higher dimension. For generic polynomial foliation in CPN, any integrable deformation of this foliation, once again parameterized by a reduced analytic space, is holomorphically trivial. An extended version of these results is presented in a book by Laura and Javier, which was edited, as I learned recently, for the second time in 2004. Now let us switch to newer results. In fact, people wish to have as much absolutely rigid foliations in the class of polynomial foliations as possible. So consider once again polynomial foliations of the projective plane AN of degree n in a fixed affine neighborhood. then in fact the set of those foliations that are absolutely rigid is real Zariski open. That is the complement to is a real algebraic manifold in the space of parameters. It was started by Sherbakov and completed by Linsneto, Sad, and Skardua in '98. Now there is a strong conjecture that covers many results, in a sense all the results above, due to Gorahani and Skardua, that I should not consider yet as a theorem rather than as a conjecture. So their conjecture sounds strikingly simple. Either the foliation has a Darboux first integral. It is a product of polynomials in complex degrees, the Darboux first integral. Or it is absolutely rigid. So the reason for non-absolute rigidity might be very tough, only integrability with the Darboux first integral. Once again, I want to show this conjecture to attract attention to it, but I would be happy if it will be a theorem. Now let us switch from the complex plane to complex projective spaces of higher dimension. What may be said about absolute rigidity in this case? Frank Loret and Giulio Rebello in '03 constructed an open set in the space of polynomial vector field of any degree higher than 1 and in any dimension, such that all the foliations from this set have the following properties. First, dense leaves in the phase space. Second, countable number of non-simply connected leaves, like cylinders. And at last, are absolutely rigid. So this is not about a generic foliation in the class considered. There is only an open set, and in a sense a rather small one, a perturbation of something that might be controlled. But still, this is the theorem, and the problem is up to what extent these properties are generic in the whole class of the foliations, of the polynomial foliations in higher dimensional projective spaces. Now, let us switch to a newer results, to rigidity of quadratic vector fields. The following notion is another version of rigidity. It is closer to the paradigm topological equivalence implies affine equivalence, yet weaker than this. A foliation is totally rigid in a certain class of foliations if it is topologically equivalent to at most a finite number of foliations from this class. If I stop here, this will have no sense, because any affine automorphism of the phase space provides a new polynomial vector field, but topologically equivalent to the previous one. So I should add modulo affine equivalence. So in the space of all foliations, the affine transformations of the phase space form a group, act as a group, and the space of foliations is split to the orbits of this group. And in fact, we speak about a finite number of these orbits when we discuss total rigidity. So, total rigidity is a much stronger notion of rigidity in comparison with an absolute rigidity. And there is a historical analogy. Totalitarian regime is much more tough than the absolutist regime. Now, let us switch back to holomorphic, to quadratic vector fields. Any singular point of a planar vector field has two eigenvalues, lambda 1 and lambda 2. We can take their ratio. But if we are taking the ratio, the eigenvalues will quarrel who will be upstairs and who will be downstairs. In order to stop this quarrel, we symmetrize the relation and take this sum. So this is the Baum-Bott index of the singular point. And the Baum-Bott relation claims that for any class of foliations, the sum of Baum-Bott indexes depends only on n, no matter what is this function for our purposes. Baum-Bott indices form topological invariants. This is a consequence of the density of leaves and the analytic equivalence of monodromic groups at infinity. So once again, I show this statement. If two foliations on CP2 are topologically equivalent and, in a sense, generic, then their Baum-Bott indices in the corresponding singular points, that is brought by the conjugacy to one another, do coincide. A theorem proved by Moldavskis and myself published in this current year claims that a generic quadratic foliation is topologically equivalent to no more than 241s modulo affine equivalence. A weaker version of this theorem with a computer-assisted proof was given by Moldavskis in his thesis 5 years ago. The present version of this theorem is in a sense a child born in Mexico. Last year there was a summer school in Mexico, in the UNAM, on analytic foliations, and I had very fruitful conversations with the participants, especially with Adolfo Guyot, and using his suggestions in particular, and using the results of Linz-Neto, this theorem was proved. Let me say a little bit more details about this theorem. We say that the Baum-Bott indices are topological invariants of a quadratic foliation. Very good. Let us take the foliation and calculate the Baum-Bott indices. How many indices do we have? As much as there are singular points. There are 4 singular points in the affine part of the projective plane and 3 at infinity. So 7 in total. And this collection of 7 numbers is a topological invariant of the foliation. Therefore, we take a foliation and we map it to C7. The image is the collection of all Baum-Bott indices, and any 2 topologically equivalent quadratic vector fields mandatorily belong to one and the same leaf of this moduli map. First of all, let us calculate the parameters. what is the dimension of the source and what is the dimension of the target. At the first glance, the dimension of the source is 12 because quadratic vector fields have 12 coefficients, and the dimension of the target is 7. Both is false. We should calculate important actual parameters on which the quadratic vector field depends. We should first factorize this space of vector fields by the multiplication by a constant factor which does not change the phase portrait, and factorize it by the 6-dimensional group of affine coordinate changes in the phase space. The factor space has dimension 5. Now we should calculate the dimension of the target. 7 singular points, but 2 relations. The first relation on the Baum-Bott indices is a linear relation, which is the Baum-Bott relation. And the second one is so-called Camacho-Sad at infinity. That is sum of quotients. Now the eigenvalues agree who is on the top and who is on the bottom. On the bottom is the eigenvalue that corresponds to the infinite leaf. So the sum of these ratios is 1, and this is the second relation. Therefore, the target space also has dimension 5. The dimensions coincide, and there is hope that the map, the Baum-Bott map, the moduli map, is algebraic, that in the class A2, the generic fiber with will be just finite. I will give a few, let me turn back here. Yet, it may happen crazily that the Baum-Bott map is just a constant map. For any quadratic vector field, the Baum-Bott indices are the same. This is crazy. But it is not very easy to prove that there is no extra relation on the Baum-Bott indices in our special class of quadratic vector fields. Linz-Netto has proved that in another class of polynomial foliations, that is polynomial foliations that have the same degree in any affine neighborhood of the projective plane, there are no extra relations on the Baum-Bott indices. Yet we need to prove this in our particular class. Adolfo Guyot proved the same statement as Linz-Netto. In fact, Linz-Netto uses his proof for the class of quadratic vector fields, once again, that preserve their degree in any affine neighborhood. We are in a slightly different class, so we have to prove this statement for nu, but we follow the ideas of predecessors. Let me probably, this frame speaks about quadratic vector fields with solvable monodromy group at infinity. I said that for generic quadratic vector fields, Baum-Bott indices are topological invariants. The main genericity assumption is solvability of non-solvability of the monodromy group at infinity. Another genericity assumption is absence of so-called complex centers. In the quadratic vector fields case, both requirements may be analyzed. Absence of centers is a famous Dulac's statement, that is, Dulac gave an explicit list of quadratic vector fields that have centers. So our second requirement is not to belong to the Dulac's list. Our first requirement is not to belong to the so-called Piartli list. And this theorem claims about a sufficient condition for non-solvability of the monodromy group at infinity. So the theorem claims the following. If all the characteristic numbers at infinity, that is ratios of eigenvalues, are non-real, then in a class of vector fields with fixed characteristic numbers at infinity, three numbers whose sum is 1, there are at most 7 quadratic vector fields with the solvable monodromy group. All the others are have non-solvable monodromy group. Unfortunately, an explicit list is not obtained. Probably it is a matter of some future research. But in any case, we know that in the quadratic case, there is very few foliations with solvable monodromy group at infinity. So any set B lambda is the set of beta lambda is the set of all quadratic vector fields with given characteristic numbers at infinity. And it contains at most 7 classes of affine equivalent foliations with solvable monodromy group at infinity. And the last thing to prove is that the Baum-Bott map has the image of dimension 5 of full dimension, not of dimension 4, say. To prove this, it is sufficient to prove that this map has a complete rank at a generic point, at least at one point. This computer-assisted proof was given by Moldavskis, but with a very slight change of the proof of Adolfo Guyot following his ideas. We prove that the rank of the Baum-Bott map is 5 almost everywhere. The reason is presented here. If it is not the case, then it is at least 4 everywhere. And there is a curve through each point in our class of quadratic foliations on which the Baum-Bott map is constant. We choose the point to be a Darboux foliation, and then using very elegant suggestions of Adolfo, one may prove that this is impossible. We get a contradiction with a suggestion that the Baum-Bott map does not change along a curve that passes through a Darboux integrable foliation. And now we can apply the Linz-Netto result that claims that if the orbit of the Baum-Bott map is 0-dimensional, not all the orbits are of this kind, then it has no more than 240 points. And together, this implies the previous theorem for quadratic vector fields. It is very interesting to prove the main paradigm for the quadratic vector fields. a generic, if two quadratic vector fields are topological equivalent, then they are affine equivalent. In fact, we know many other topological invariants except for bound-Bott indices. These are Taylor coefficients of the monodromy transformations at infinity. So if we prove that these invariants are different along a generic orbit of the bound-Bott map, then we are done. This is, once again, a matter of future investigation. What about higher degree? We are now in the class AN, and in the higher degree, we have a weaker result that I will probably not discuss in details because of the lack of time. The claim is that we have a similar but weaker theorem for polynomial vector fields of higher degree. Yesterday, I had a discussion with Valente Ramirez, and he presented me very elegant ideas that might improve this result. I do not present these ideas, but I want just to encourage Valente to go on. Now, a few words about the higher dimension of the phase space. This is a last brief section of my talk. What about rigidity for polynomial vector fields in the spaces of higher dimension? 3 or more. In dimension 3 or more, there is an effect which was quite unexpected in 70s and discovered independently by a Minsk mathematician Ladis and Camacho Kuiper Palles. The effect is the following. Even generic complex linear foliations have topological invariants. And the topological invariants are listed here. These are periods of let us just call these quantities 1 over lambda j is the inverse eigenvalue of the singular point. Let us call these quantities periods, and they are R-linear equivalent. That is, you take the tuple of all the periods. You want to understand whether two foliations are topological equivalent or not. You take two tuples. These are two, say, triples of complex numbers, and you ask whether there is a real linear operator that brings one triple to another. You can take an operator that will bring the first couple to another one, but then the operator will be completely defined, and the third element in the triple may be brought to the third element of the second triple or not be brought. And this is the invariant. So this is an explanation of the previous theorem. And in the complex domain, there is a sort of Grobman-Hartmann theorem that is complex hyperbolic germ of a vector field is topologically equivalent to its linear part. This is the theorem due to Chaperon. Now we get once again moduli of topological equivalence. Counting dimensions shows that the dimension of the target is larger than the dimension of the source, and this gives us to make the same reasoning about the fibers of the moduli map as we have done before. And for quadratic vector fields in C5, Moldavskis proved that the moduli map has the full rank. This is once again a computer-assisted proof, and it is a challenge to find an analytic one. And the corresponding moduli map has the full rank, and therefore the topological rigidity, even the total rigidity in the space of quadratic vector fields in C5 is proved. Now I should mention a result which strangely is new. Looking at this frame, you can forget about everything preceding. This is just a following question. You take a polynomial, you take its roots, and you take the values of the derivative of the polynomial at these roots. It is sort of eigenvalues of singular points of one-dimensional vector field. What is the rank of this map? Zarhin proved recently that the rank is n-1 at generic points. The question is to generalize this to higher dimension. We take a vector field in any space of any degree in any dimension. We take singular points. We take spectra at these singular points, and we ask about the rank of this map. I guess that there is no answer, and it is interesting to, I believe that the rank is full. So if this is true, then we have total rigidity for polynomial vector fields in higher dimensions. Once again, congratulations to Xavier and thanks. Yes?
I'd like to know if you think of this as being something positive or negative. Are you happy with rigidity or not? Because if you look at three dynamical systems, you have the same dream that maybe the generic dynamical system could be structurally stable. It was not. And then people had to find new tools, like stochastic stability. So my next question would be, if we have this rigidity in general, what can we do?
I agree that this is quite a different question. So, in a very global perspective, all this subject is in a sense pessimistic. In my youth, I stated this paradigm and I was like to investigate it. But in a sense, it gives us only the information that topological equivalence and structural stability, which is so fruitful in the real setting, is not at all fruitful in the complex setting. And I appreciate the question of Etienne, what's to do, but it was not my goal today. And in fact, I think, for instance, that the result of relatively recent result of Victor Klepsin and Bertrand de Rouen is a step in this way. Results of Sibony and Fornaes in the same direction are also steps. So there is another activity, yes, there is another realm of activity which gives positive information in comparison to this negative one. Yes.